Okie dokie. Ready to resume on chapter 31. We are on page 655. It is 6:03. All right, let's get after it here. All right, threads, thread safety, and per thread storage. Excuse me. All right, this chapter extends the discussion of the POSIX Threads API, providing a description of thread-safe functions and one-time initialization. We also discuss how to use thread-specific data for thread local storage to make an existing function thread safe without changing the function's interface. Just throw a mutex on it. Thread safety and reentrancy revisited. So again, to resume this conversation about reentrancy, thread safety, and what they refer to as async signal safe. My understanding is that thread safety is the weakest of constraints, and then reentrancy is like a more strict set of constraints, and then async signal safe is the most extreme form of constraints. And if you're async signal safe, you are reentrant and you're thread safe. If you're a reentrant, I'm pretty sure you're thread safe. I'm pretty sure that's the relationship. But thread safety, basically, you're not racing on data. The code can be executed by multiple threads, at concurrently. And that could be achieved through like mutual exclusion locks, through condition variables, through semaphores, through atomic operations, atomics types, stuff like that. But reentrancy also requires, what is it that requires? That the same thread can execute. So if you're in a specific thread, that same thread, either in a call, like a recursive call, or in a call from a signal handler, it can re-enter the same function from the same thread, and it's still safe. It's not sharing any data structures. Also, like for something to be reentrant, you also have to make sure that the pointers that are being returned by that code are not static variables that are being mutated every time you invoke the code. So if I get a pointer back from that code, then I call that code again and get another pointer back, then that second invocation shouldn't affect the first. So that's like another aspect of reentrancy. And then async signal safe basically means like it's safe to be put into a signal handler, and it involves like a lot more constraints that are documented. I'm not going to go into. So that is my preface of like where my head is at as far as like the relationship between thread safety, reentrancy, and async signal safe code. A function is said to be thread safe if it can safely be invoked by multiple threads at the same time. Conversely, if a function is not thread safe, then we can't call it from one thread while it is executed in another thread. For example, the following function, similar to code that we looked at in 31, is not thread safe. So we got a static integer glob, a global thing, and then we have a increment function that increments a number of loops. Sorry, I skipped ahead a page here. Yeah, so that is no bueno, because you got global state that you're mutating concurrently from the same function. If multiple threads invoke this function concurrently, the final value of glob is unpredictable. The function illustrates a typical reason that a function is not thread safe. It employs global or static variables that are shared by all threads. There are various methods of rendering a function thread safe. One way is to associate a mutex with a function, or perhaps with all the functions in the library, if they all share the same global variables. Lock that mutex when the function is called and unlock it when the function returns. This approach has a virtue of simplicity. On the other hand, it means that only one thread at a time can execute the function. We say that across access to the function is serialized. If a thread spends a significant amount of time executing this function, then this serialization results in a loss of concurrency because the thread of the program can no longer execute in parallel. More sophisticated solutions is to associate the mutex with a shared variable and then determine which parts of the function are critical sections that access the shared variable and acquire and release the mutex only during the execution of these critical sections. This allows mutex threads to execute the function at the same time and to operate in parallel, except when more than one thread needs to execute a critical section. Non-thread safe functions. To facilitate the development of threaded applications, all the functions specified in SUSV 3 are required to be implemented in a thread safe manner, except those listed in table 31.1. Many of these functions are not discussed in this book. In addition to the functions listed in 31.1, SUSV 3 specifies the following. The C term ID and temp nam functions need not be thread safe if pass a null argument. The WCR, TOMB, and whatever functions need not be set thread safe if their final argument is PS is null. SUSV 4 modifies the list of function table 31.1 as follows. I don't really care. The standards do not prohibit an implementation from making the functions in table 31 thread safe. However, even if some of these functions are thread safe on some implementations, a portable application cannot rely on this to be the case on all implementations. Oh, great. I typed the wrong character again. So we're on 657, which is somewhere. Nope. There we go. Reentrant and non-reentrant functions. Although the use of critical sections to implement thread safety is a significant improvement over the use of per function mutexes, it's still somewhat inefficient because there is a cost to locking and unlocking mutexes. A reentrant function achieves thread safety without the use of mutexes. It does this by avoiding the use of global and static variables. Any information that must be returned to the caller or maintained between calls of the function is stored in buffers allocated by the caller. Refers to counter reentrancy and discussing the treatment of global variables and signal handlers in section 21.1.2. However, not all functions can be made reentrant. The usual reasons are the following. By their nature, some functions must access global data structures. The functions in the malloc library provide a good example. These functions maintain global linked list of free blocks on the heap. The functions of the malloc library are made thread safe through the use of mutexes. Some functions defined before the invention of threads have an interface that by definition is non-reentrant because they return pointers to storage statically allocated by the function, or they employ static storage to maintain information between successive calls of the same or related function. Most of the functions in table 31.1 fall into this category. For example, the ASC time function returns a pointer to a statically allocated buffer containing a datetime string. Silly. Okay. For several of the functions that have non-reentrant interfaces, SUSV 3 requires reentrant equivalents with names ending with the suffix R. These functions require the caller to allocate a buffer whose address is then passed to the function and used to return the result. This allows the calling thread to use a local stack variable or for the function results buffer. For this purpose, SUSV 3 specifies ASC time R. All the underscore. Some implementations also provide additional reentrant equivalents of other traditional non-reentrant functions. For example, glibc provides crypt R, get host by name R, get served by name R, get utent R, get UTID, get UT line R, and so. However, a portable application can't rely on these functions because being present On other implementations, in some cases, Substitute 3 doesn't specify these reentrant equivalents because alternatives to the traditional functions exist that are both superior and reentrant. For example, get attr info is the modern reentrant alternative get host by name and get serve by name. One-time initialization. Sometimes a threaded application needs to ensure that some initialization action occurs just once. Regardless of how many threads are created. For example, a mutex may need to be initialized with special attributes using pthread, mutex, init, and that initialization must occur just once. If we are creating the threads from the main program, then this is generally easy to achieve. We perform the initialization before creating any threads that depend on the initialization. However, in a library function, it's not possible because the calling program may create the threads before the first call to the library function. Therefore, the library function needs a method of performing the initialization the first time that it is called from any thread. A library function can perform one-time initialization using the pthread once function. Yeah, there's a once function in Go. The pthread once function uses the state of the argument once control to ensure that the caller defined function pointed to by init is called just once, no matter how many times or from how many different threads the pthread once call is made. The init function is called without any arguments and thus has the following form: void init function body. The once control argument is the once control argument is a pointer to a variable that must be statically initialized with the value pthread once t. Pthread once t, once var, pthread once init. If first call to pthread once, that specifies a pointer to a particular pthread once t variable, modifies the value of the variable pointed to by once control so that subsequent calls to pthread once don't invoke init. One common use of pthread once is in conjunction with thread specific data, which we describe next. Thread specific data. The main reason for the existence of pthread once is that in early versions of pthreads, it was not possible to statically initialize a mutex. Instead, the use of pthread, mutex, init was required. Given the later addition of statically allocated mutexes, it was possible for library functions to perform one-time initialization using a statically allocated mutex and a static Boolean variable. Nevertheless, pthread once is retained as a convenience, thread-specific data. The most efficient way of making a function thread safe is to make it reentrant. All new library functions should be implemented this way. However, for an existing non-reentrant function, one that was perhaps designed before the use of threads became common, this approach usually requires changing the function's interface, which means modifying all of the programs that use the function. Thread-specific data is a technique for making existing function thread-safe without changing its interface. A function that uses thread-specific data may be slightly less efficient than a reentrant function, but allows us to leave the program that called the function unchanged. Thread-specific data allows a function to maintain a separate copy of a variable for each thread that calls the function. As illustrated in figure 31.1, thread-specific data is persistent. Each thread's variables continues to exist between the thread's invocation of the function. This allows the function to maintain per thread information between calls to the function and allows the function to pass distinct result buffers if required to each calling thread. So thread A, thread specific data buffer for my func. Yeah, it's different buffer. Okay. It's kind of a pointless diagram. All right, thread-specific data from the library's function perspective. In order to understand the use of thread-specific data API, we need to consider things from the point of view of a library function that uses thread-specific data. The function must allocate a separate block of storage for each thread that calls the function. This block needs to be allocated once. the first time the thread calls the function. On each subsequent call from the same thread, the function needs to be able to obtain an address of the storage block that was allocated for the first time this thread called in the function. The function can't maintain a pointer to the block in an automatic variable, since the automatic variable disappears when the function returns, nor can it store a pointer in a static variable, since only one instance of each static variable exists per process. pthread API provides functions to handle this task. Different, i.e. independent functions may each need thread-specific data. Each function needs a method of identifying its thread-specific data, a key, as distinct from the thread-specific data used by other functions. The function has no direct control over what happens when the thread terminates. When the thread terminates, it's probably executing code outside of the function. Nevertheless, there must be some mechanism, a destructor, to ensure that the storage block allocated for this thread is automatically deallocated when the thread terminates. If this is not done, then memory leak could occur as threads are continuously created. Call the function and then terminate. So I guess I always thought thread-specific data is statically allocated. Like when you set up the stack for the thread, you also have like a little spot where you have like kind of like the data section where you like to say, hey, here's all the memory that you asked for that's needed by the code here. But I guess since threads are dynamically created, you wouldn't know what code it's invoking in advance, and so you wouldn't know what thread specific data would be needed in advance, so it has to be allocated on the heap. Yeah, I think it has to be allocated. It can't be. I guess one way that you could do it is have like the static data section just copied on the top of the stack for every thread, and then most of it's not gonna be used. But like, I guess you could do that, yeah. Yeah, I think you could do that. You could say every function that's being linked in this program, compiled and linked, tell me which of your variables not only are static, which will go in the data section, but like which one of your variables are thread local. And then it'll get an entry in the data section with the static variables, but it'll also get an entry every time you create a thread stack. So I guess you don't have to do it on the heap. You could do it on the stack if you do that. Do it that way. Overview of the thread-specific data API. The general steps that the library function performs in order to use thread-specific data are as follows. A function creates a key, which is the means of differentiating the thread-specific data item used in this function from the thread-specific data items used by other functions. The key is created by calling pthread key create function. Creating a key needs to be done only once when the first thread calls the function. For this purpose, pthread once is employed. Creating a key doesn't allocate any blocks of thread-specific data. The call to pthread key create serves a second purpose. It allows the caller to specify the address of the program-defined destructor function that is used to deallocate each of the storage blocks allocated for this key. See the next step. When the thread that has thread-specific data terminates, the pthreads API automatically invokes the destructor, passing it a pointer to the data block for this thread. The function allocates a thread-specific data block for each thread from which it is called. This is done using malloc or a similar function. This allocation is done once for each thread, the first time the function is called. In order to save a pointer to the store, so it's using malloc and free, it's on the heap. In order to save a pointer to the storage allocated in the previous steps, the function employs two pthread functions, pthread set specific, pthread get specific. A call to pthread set specific is a request to the pthread's implementation to say, save this pointer recording the fact that it is associated with a particular key, the one for this function, and a particular thread, the calling thread. Calling get get specific performs a complementary task, returning the pointer to previously associated with the given key for the calling thread. If no pointer was previously associated with a particular key and thread, then pthread get specific returns null. This is how a function can determine that it is being called for the first time by the thread, and thus must allocate the storage block for the thread. Okay, I like to see a usage of that. So we got key create, get specific, a diagram, and then we got some code. Okay, we got some code examples. They got a lot of code examples. But this isn't thread local storage, this is something else. Thread specific data. Details of thread specific data API. Excuse me. In this section, we provide details of each of the functions mentioned in the previous section that elucidate the operation of thread specific data by describing how it is typically implemented. The next section shows how to use thread-specific data to write a thread-safe implementation of the standard C library function strErr. Calling pthread key create creates a new thread-specific data key that is returned to the caller in the buffer pointed to by key. Okay, so you say, hey, create my key. Here's a destructor. Because the return key is used by all threads in the process, key should point to a global variable. The destructor argument points to a programmer-defined function of the following form. Destructor. Upon termination of the thread that has a non-null value associated with the key, the destructor function is automatically invoked by the pthreads API and given that value as its argument. The passed value is normally a pointer to the thread-specific data block for this key. A destructor is not required, then, if a destructor is not required, then destructor can be specified as null. If a thread has multiple thread-specific data blocks, then the order in which the destructors are called is unspecified. Destructor functions should be designed to operate independently of one another. Looking at the implementation of thread-specific data helps us understand how it is used. A typical implementation NPTL is typical, involves the following arrays: a single global process-wide array of information about thread-specific data keys, and a set of per-thread arrays, each containing pointers to all the thread-specific data blocks associated for a particular thread. In this implementation, the pthread key t value returned by pthread key create is simply an index into the global array, which we label pthread keys, whose form is shown in 31.2. Each element in this array is a structure containing two fields. First field indicates whether the array element is in use. Second field is used to store the pointer of the destructor function for the thread-specific data block for this key. Okay. Implementation of thread-specific data keys. The pthread set specific function requests the pthread's API to save a copy of value in a data structure that associates it with the calling thread with the key returned by previous call to key create. The get specific function performs a converse operation returning the value that was previously associated with the given key for this thread. So we say, hey, set specific key value, get specific key, return value. The value argument given to set specific is normally a pointer to a block of memory that has previously been allocated by the caller. This pointer will be passed as an argument to the destructor function for this key when the thread terminates. The value argument doesn't need to be a pointer to a block of memory. It could be some scalar value that can be assigned with a cast to void star. In this case, the earlier call to pthread create would specify destructor as null. Figure 31.3 shows a typical implementation of the data structure used to store value. In this diagram, we assume that pthread keys was allocated to a function named myfunc. For each thread, the pthreads API maintains an array of pointers to thread-specific data blocks. The elements of each of these thread-specific arrays have one-to-one correspondence with the elements of the global pthread keys array, shown in Figure 31.2. The pthread set-specific function sets the element corresponding to the key in the array for the calling thread. So all correspond to pthread keys 1. So then we got value of key 1 for thread A, value of key, yeah, so you got the different threads. Wait a minute. Corresponding to pthread keys 1. Data structure used to implement threads. I wish you'd just give me the data structure because this visual is not helpful. Okay. I don't like this API. It sucks. I don't like it. It relies very heavily on malloc and free heap. Like I would want to have the ability to allocate this memory as part of the thread stack, like before the stack memory. So that's like a big thing. Yeah. I mean, that's the biggest issue I have, is that it's focuses on heap allocation with malloc and free. When a thread is first created, all of its thread-specific data pointers are initialized to null. This means that when our library function is called by a thread for the first time, it must be using pthread getSpecific to check whether the thread already has an associated value for key. If it does not, then the function allocates a block of memory and saves a pointer to the block using pthread setSpecific. We show an example of this in the thread-safe stir error implementation presented in the next section. Employing the thread-specific data API. When we first described the standard stir error function in section 3.4, we noted that it may return a pointer to a statically allocated string as a function result. This means that stir error may not be thread safe. In the next few pages, we look at a non-thread safe implementation of stir error and then show how thread specific data can be used to make this function thread safe. Sounds good. On many Unix implementations, including Linux, the stir error function provided by a standard C library is thread safe. However, we use an example of stir error anyways because SSV3 does not require this function to be thread safe, and its implementation provides a simple example of the use of thread safe specific data. Listing 31.1 shows a simple non-thread safe implementation of stir error. The function makes the use of a pair of global variables defined by glibc. Sys error list is an array of pointers to strings corresponding to error numbers in error node. Thus, for example, sys error list inval inval points to the string invalid argument, and sys error specifies the number of elements in the error list. Okay, so let's go over the implementation here. So the main thing here is we're defining max error length to be 256. So that gives us a way of letting the compiler know that it's not going to be any longer than that. So we don't have to do any dynamic allocation. So we set up our buffer, static character buffer, max error length. So this is the statically allocated memory that's going to be returned. And then we say, okay, stir error for int error if error is less than 0 or error is greater than or equal to sys n errors, then we don't have a valid string for this thing. Or when we index into it, it was set to equal to null. Then we say unknown error. Else we do a stir n copy from sys errorless error into buffer with the max error length -1 as the number of bytes to copy. And then we, of course, set our buffer last character to be 0, so that we always ensure there's a null termination and return the buffer. Okay, makes sense. We can use the program listing 31.2 to demonstrate the consequences of the fact that the stir error implementation listing 31.1 is not thread safe. This program calls stir error from 2 different threads, but displays the return value of only after both threads have called stir error, even though each thread specified a different value as an argument to stir error. This is what we see when we compile and link this program with a version of stir error listed in 31.1. The main thread, and then other thread, and they both have operation not permitted. Both threads display error no string corresponding eperm, because the call to stir error on the second thread in thread func overwrote the buffer that was written by the call to stir error on the main thread. Inspection of this output shows that the local variable stir in the 2 threads points to the same memory address. So like the easy way to solve this thing in like Go would be to just like do an allocation, like allocate heap memory and return a pointer to it. And then of course Go's garbage collector can take care of freeing that memory and do a bunch of escape analysis and optimizations to like minimize the cost of that. But that would be the way that you would solve this in Go. You just say like, hey, or you could return a pointer to the statically allocated memory. Sorry. Let me rephrase that. We return a pointer to the data section where the string is originally, because like what you're doing here is you're like copying. If I go back page, you're doing a copy from where the data exists in the data section to the buffer that is being shared between invocations. So instead of doing that, why don't you just return the pointer here, you know? And make it read-only, because it'd be part of the read-only data section. I mean, I think that's the thing to do here. And if they want to write to the string and mutate it, they got to make a copy of it. I think that's the way to fix that. Just don't even do this copy for them. But yeah, in Go you could do the copy into a new structure and then return it, a pointer to it, and then escape analysis will mean that it gets allocated on the heap, and then the garbage collector would take care of it. Excuse me. All right, where are we at here? Let's start from the beginning here. Both threads display error notice string corresponding to eperm because the call to stir error by the second thread over the buffer that was written to call the main thread. Inspection of the output shows that the local variable stir and the 2 threads point to the same memory address. Exactly. So this is calling it from 2 different threads. It's just a program that we just saw. Listing 31.3 shows a reimplementation of stir error that uses thread-specific data to ensure thread safety. The first step performed by the revised stir error is a call to pthread once to ensure that the first invocation of this function from any thread calls create key. The create key function calls pthread create to allocate thread-specific data. I'm not going over this line-by-line breakdown. I'll just read the code, thank you. So pull in pthread. We create the once that we need to generate the key, and then we create the key. Create key is the one-time function. Destructor is just a free on the buffer. Once is a key create to the, wait a minute, stir error key. Wait a minute. Okay, that's here. Yeah, stir error key. and then it's given the destructor. Yep, all makes sense. And then our stir error, we go into here, we do our once to create the key. And now that the key exists, we can reference it. We're guaranteed for this to happen once per thread because it's a p thread once. I think goes once is a no, the p thread once. No, that's for per process. It runs once per process because you don't need to recreate the key for every thread. The key is shared between all the threads. Okay, so but the point is, by the time we get down to here, either it was created by pthread once getting invoked, or the other threads were blocked waiting on the pthread once to complete. I think that's the way that works. I don't think you can get past this once without it having already ran and completed. Not started, but completed. Okay, so pthread gets specific stir error, so we know that this is good. Pthread gets specific. So now we get our buffer back. And then if buffer is equal to null, because it might just be null on the first run, then we malloc up our buffer and we set it. And since these are per thread, there's no racing with other threads for these. And then this is just some of the same logic that we saw before to figure out if the value is known, and then the copy into the buffer this time, and then the return of the buffer. And so next time you call stir error, it's going to reuse that buffer. It's going to call get specific, get the buffer back. So this is not reentrant, it's just thread safe. If we compile and link our test program with the new version of stir error to create an executable file, then we see the following results in the running program. Yep. From this output, we see that new version of stir error is thread safe. We also see that the address pointed to by the local variable stir in the two threads is different. Thread specific data limit implementation limits. As implied by our description of how thread-specific data is typically implemented, an implementation may need to impose limits on the number of thread-specific data keys that it supports. SB3 requires that an implementation support at least 128 keys. An application can determine how many keys an implementation actually supports either via the definition of pthreads keys max or by calling scthreads keys max. Linux supports up to 1024 keys. Even 128 keys should be more than sufficient for most applications. This is because each library function should employ only a small number of keys, often just one. If a function requires multiple thread-specific data values, these can usually be placed in a single structure that has just one associated thread-specific data key. I don't know about that. Could you do that? I guess you could. Yeah, you could do that. That sounds good. I was worried, like, if you did that, would it cause situations where you have two bits of code, one that wants one part of the struct, the other part of the code wants the other part of the struct, but if it's all shared within the same thread and not shared across other threads, then only one bit of the code is going to be ran at once in that thread, so it's not going to be racing with itself or anything. Thread local storage. Okay, so they were saying that the issue is that there's not enough, because of the way that it's implemented, there's not enough, well, there's a limit on the amount of thread specific data keys. My issue is that it relies heavily on heap allocation, and I wanted something that was more stack focused, or where the memory is allocated as part of the thread stack. Like thread-specific data, thread local storage provides persistent per-thread storage. This feature is non-standard, but is provided in the same or a similar form on many other Unix implementations, e.g. Solaris and FreeBSD. The main advantage of thread local storage is that it's much simpler to use than thread-specific data. To create a thread local variable, we simply include underscore thread specifier in the declaration of the global or static variable. Yep, exactly. Each thread has its own copy of the variable declared with the specifier. The variable in the thread's local storage persists until the thread terminates, at which time the thread's storage is automatically deallocated. Note the following points about the declaration of and use of thread local variables. The thread keyword must immediately follow a static or extern keyword if either of these is specified in the variable's declaration. The declaration of a thread local variable can include an initializer in the same manner as normal global or static variable declarations. Okay. The C address operator can be used to obtain the address of a thread local variable. Okay. Thread local storage requires support from the kernel, provided in Linux 2.6. The pthreads implementation provided in NPTL and the compiler provided. Listing 31.4 shows a thread-safe implementation of stir error using thread local storage. If we compile and link our test program with this version of stir error to create an executable file, stir error test TLS, then we see the following result when running the program. Different memory addresses, exactly. Oops, sorry. Thread safe implementation stir error. So basically just added underscore thread to it and it works now. Summary. A function is said to be thread safe if it can safely be invoked. See, they didn't really discuss where this memory is. So I got to ask AI about this. So we say, hey, with thread local storage, when you declare a static global variable with underscore thread, where exactly relative to the thread's stack is that memory stored? I'm thinking that regular global static variables are in the data section of the section, but because threads can be created dynamically at runtime, this space cannot be made for these static thread global variables there because it is so they gotta go somewhere, and I figure it would be relative to the thread stack. Per thread TLS blocks allocated and managed by the runtime loader, typically via the threaded control block. This is a whole new thing. Their location is fixed relative to the thread control block, not relative to the stack. You're right about ordinary global, static global variables, data BSS. One instance per process. Address is fixed at program load time. What changes with thread and thread local? When you write thread, you're saying this is 1x per thread, but its identity is still global. Same symbol name. that forces the implementation to do something more clever. The key ID, thread local storage, is its own storage class. TLS variables live in a TLS segment, not data or BSS or the stack. Conceptually, every thread has thread stack, thread local storage, a thread control block. Exact ordering varies by architecture in libc, but TLS is anchored off the TCB, not the stack. How the address of a TLS variable is computed. When a compiler sees, hey, it does not generate a normal absolute address. Instead, it generates something like thread pointer plus constant offset. Okay, the thread pointer points at the thread control block. Each TLS variable gets a fixed offset within the TLS block. That offset is the same for every thread. Yeah. So you got to figure out where your block is, and then you get an offset. Good instinct. This happens at thread creation. pthread create asks the runtime to create a thread. The runtime allocates a stack, allocates a TLS block, sets up the CCB, initializes TLS variables. Kernel starts the thread with stack pointer and a thread pointer. So although the layout TLS is fixed at link time, storage is allocated per thread at runtime. Putting TLS on the stack would be disastrous. I'm not saying putting it on the stack, I'm saying putting it before the stack. Okay, so on Linux glibc, TLS is typically allocated adjacent to the thread stack, but is not defined to be before the stack in any architectural or ABI sense. It is defined relative to the thread pointer, not the stack base. Okay, I don't really like the way AI is going over this. All right, where am I at? I guess we're in this summary. All right, we're already done with this. Okay, the function is set to be thread safe if it can safely invoke from multiple threads at the same time. The usual reason that a function is not thread safe is that it makes use of global static variables. One way to render a non-thread safe function safe in multi-thread applications is to guard all calls on the function and mutex lock. This approach suffers a problem that reduces concurrency because only one thread can be in the function at the same time. An approach that allows greater concurrency is to add mutex locks around those parts of the function that manipulates shared variables, the critical sections. Mutexes can be used to render most functions thread safe, but they carry a performance penalty because there's a cost of locking and unlocking mutex. By avoiding the use of global and static variables, a reentrant function achieves thread safety without using mutexes. Most of the functions specified in SUSV3 are required to be thread safe. SUSV3 also lists a small set of functions that are not required to be thread safe. Typically, these are functions that employ static storage to return information to the caller or maintain information between successive calls. By definition, such functions are not reentrant, and mutexes can't be used to make them thread safe. We consider two roughly equivalent coding techniques: thread-specific data and thread local storage, that can be used to render a unsafe function thread safe without needing to change its interface. Both of these techniques allow a function to allocate persistent thread per thread storage. Further information refers to the sources of further information, blah, blah. Implement a function, not gonna do that. Use thread specific data to write threads safe version of so-and-so. Not gonna do that. So we are at 32, which is 672. We got pretty far. 55, 65, it's almost, what, 17 pages? That went by really fast. 652. I guess because I'm familiar with these concepts and I'm not doing any of the exercises. I don't know. It seems like I read a lot of that really quickly. All right, let's finish this up then. Next page, thread cancellation. And I think I got about 8 pages left. So I will definitely be done before 7:30, I think. All right, thread cancellation. Typically, multiple threads execute in parallel with each thread performing its task until it decides to terminate by calling pthread exit or returning from the thread start function. Sometimes it can be useful to cancel a thread, that is, to send it a request asking it to terminate now. This could be useful, for example, if a group of threads is performing a calculation and one of the threads detects an error condition that requires the other threads to terminate. Alternatively, a GUI-driven application may provide a cancel button to allow the user to terminate a task that has been being performed by a thread in the background. In this case, the main thread controlling the GUI needs to tell the background thread to terminate. In this chapter, we describe the POSIX threads cancellation mechanism. So, cancellation in Go is typically provided via context. You have a shared context or context tree that is shared between multiple threads or Go routines, and there's the ability for the context to be canceled. And when it's canceled, not only is the context root node canceled, but all of its children are also canceled. And the Go routines have to cooperate in checking their canceled status periodically, and if they detect, oh, I've been canceled, then they gotta clean up shop. So it's more of a cooperative mechanism versus a non-cooperative, what do they call it? What do they call it? Am I tired? Why can't I think of this? You have cooperative scheduling, and then you have all right, AI, you gotta help me out here. What is the type of scheduling where the routines do not need to cooperate? It's not. Preemptive. I don't know why my brain was like not coming up with that word. Anyways, it would be nice if you could just preempt the thread and be like, you're scheduled off the CPU and you're terminated. There's nothing you can do about it. But that might mess up some, like, with the pthread API especially, it might mess up some of the like destruction of the thread. There's like I think pthreads has like a finalizers or something. Oops. Does pthreads have a concept of finalizers per thread? Destructors, yeah. You give it a destructor when you create the thing. So if the thread needs to run its destructor when it's exiting, then, and you just preempt it, it wouldn't be able to run its destructors and do any other cleanup that it needs to do. All right. Sometimes it can be useful to cancel a thread, that is to send a signal. Yeah. Okay. The pthread's cancel function sends a cancellation request to the specified thread. Notice it's a request, so it's cooperative. Having made the cancellation request, pthread cancel returns immediately. That is, it doesn't wait for the target thread to terminate. Precisely what happens to the target thread and when it happens depends on that thread's cancellation state and type as described in the next section. Cancellation state and type. The pthread set cancel state and pthread set cancel type functions set flags that allow a thread to control how it responds to a cancellation request. So you got these things called set cancel state and set cancel type. The pthread set cancel state function sets calling thread's cancelability state to the value given in state. This argument has one of the following values. Cancel disabled, the thread is not cancelable. If a cancellation request is received, it remains pending until cancelability is enabled. Cancel enabled, opposite, thread is cancelable. This is the default cancelability state in newly created threads. The thread's previously cancelability state is returned in the location pointed to by old state. So you can set its type. If we're not interested on the previous cancelability state, Linux allows old state to be specified as null. This is the case on many other implementations as well. However, Costudying doesn't specify this feature, so portable applications can't rely on it. We should always specify a non-null value of old state. Temporarily disabling cancellation. Pthread cancel disable is useful if the thread is executing a section of code where all the steps must be completed. Like going into mutex or something, you have a critical section, you don't want the state to get like corrupted in the middle of it, maybe. If a thread is cancelable, pthread cancel enabled, then the treatment of the cancellation request is determined by the thread's cancelability type. Which is specified by the type argument in the call to pthread set cancel type. This argument has one of the following values: asynchronous deferred. Asynchronous, the thread may be canceled at any time, perhaps, but not necessarily immediately. Asynchronous cancelability is rarely useful, and we defer discussion of it until 32.6. Deferred, the cancellation remains pending until a cancellation point. We see the next section is reached. This is the default cancelability type in a newly created thread. We say more about deferred cancelability in the following sections. The thread's previous cancelability type is returned in the location pointed to by old type. As with set cancel state, old state argument, many applications including Linux allow old type to be specified as null if we were not interested in the previous cancelability type against blah blah. Okay. When a thread calls fork, the child inherits the calling thread's cancelability type and the state. When the thread calls exec, the cancelability state and type of the main thread of the new program reset to enable and deferred respectively. Cancellation points. This is where like the mutex stuff, right? When cancelability is enabled and deferred, a cancellation request is acted upon only when the thread reaches a cancellation point. The cancellation point is a call to one of the set of functions defined by the implementation. Subset 3 specifies that the functions shown in table 32.1 must be cancellation points if they are provided by an implementation. Most of these functions that are capable of blocking the thread for an indefinite period of time. Okay. Basically all the blocking stuff. In addition to the functions, Subset 3 says a larger group of functions that an implementation may define it as cancellation points. These include deal open, a bunch of other stuff. I was curious, like if I acquire a lock and I'm in a critical section, I don't want to get canceled because I did a read or something. I guess a read you wouldn't want to do in a lock. What might you want to do in the lock? A nano sleep, or a close perhaps, or message receive. I think a read, you might, it's not always a good idea to read because read can block forever and hold the lock open. But say you acquire a lock and they do one of these things, these cancellation points, and in that critical section, there's like an incomplete state, then you would be canceled, leaving the lock closed and leaving the state incomplete or in an invalid state. So I don't know. I hope they cover that. Various functions that retrieve information from system files such as utemp file. A portable program must correctly handle the possibility that a thread may be canceled when calling these functions. Substitute theory specifies that aside from the two lists of functions that must and may be cancellation points, none of the other functions in the standard may act as cancellation points. i.e., a portable program doesn't need to handle the possibility that calling these other functions could precipitate thread cancellation. Sorry, I'm just like, my brain's wandering right now. I'm thinking about Zig, and like they're going through this huge rewrite, the IO rewrite, where they're handling concurrency stuff and async await and everything. And I'm thinking about Go, and I'm like, Rob Pike had decades of trial and error implementation, deep dive into like concurrency and like how to do it right. And this like Andrew guy has like maybe a couple years to get it done and get it right. I think that's why all these other languages don't have as good a concurrency model as Go, is that Rob Pike and like some of these other dudes, they just spent decades experimenting and going deep in this stuff, you know? Like they were not inexperienced when they wrote Go. Go was like the culmination of decades of experience. All right, substitute 3 specifies that aside from the two lists of functions that must and may be cancellation points, none of the other functions in the standard may act as cancellation points. Okay. Substitute 4 adds open at to the list of functions that must be a cancellation point and removes sig pause. It moves to the list of functions that may be cancellation points and use sleep, which is dropped from the standard. An implementation is free to mark additional functions that are not specified in the standard as cancellation points. Any function that might block, perhaps because it might access a file, is a likely candidate to be a cancellation point. With glibc non-standard, many non-standard functions are marked as cancellation points for this reason. Upon receiving a cancellation request, a thread whose cancelability is enabled and defer terminates when it next reads a cancellation point. If a thread was not detached, then some other thread in the process must join it in order to prevent it from becoming a zombie thread. When a canceled thread is joined, the value returned in the second argument to pthread join is a special thread return value pthread cancel. That's the one you gotta look out for. So we got testing for thread cancellation, cleanup handlers, example program, asynchronous cancelability. I'm curious, The mutex remains locked. Critical section may have be half executed. Any shared state protected by the mutex may be inconsistent. Other threads may deadlock forever. So yes, your intuition is correct. Cancellation is intentionally low level and dangerous. I didn't see it as a cancellation point. It was not listed in the book here. Let's go ahead and read man, foreground here, do another terminal. Man, pthread, mutex, lock, cancellation. It says here, none of the mutex functions is a cancellation point, not even pthread mutex lock. AI, you're a liar. I misspoke earlier. Of course you did. I think this is a wise thing to do. Disable cancellation while holding mutexes. Just disable it. I'm going into a critical section. Disable. Can't cancel me. That's hard to enforce. And this is just annoying to deal with. Cleanup handlers. That's not great. I'd rather just disable cancellation than do all this nonsense. Okay, basically, I hope that he touches on this, because if he doesn't mention that, then it's very easy for someone who reads this book to be like not aware of the hazard there, where you acquire a mutex, you're in a critical section, you get canceled. Okay, example program, listing 32.1. Shows a simple example of the use of pthread cancel. The main program creates a thread that executes an infinite loop, sleeping for a second and printing the value of the loop counter. The thread will only terminate if it has sent a cancellation request or if the process exits. Meanwhile, the main program sleeps for 3 seconds and then sends a cancellation request to the thread that it created. When we run this program, we see the following. Pthread cancel, new thread started, loop 1, 2, 3, thread was canceled. Give me 1 second here. Then we'll go over the program. Just need to type something up here. Okay, okie dokie. Let's continue onward here. So we were on the example program. We were reading it. It does exactly what we said it did. Create a thread, sleep for 3 seconds, cancel the thread, join it. And then in the thread, we loop forever, incrementing j, sleeping every second. And we're going to be stuck in this loop forever, and it's going to get canceled at the sleep, basically. Because sleep is a cancellation point. Test for thread cancellation. In listing 32.1, the thread created by main accepted the cancellation request because it executed a function that was a cancellation point. Sleep is a cancellation point. Printf may be 1. However, suppose a thread executes a loop that contains no cancellation points, a compute bound loop. In this case, the thread would never honor the cancellation request. The purpose of pthread test cancel is simply to be a cancellation point. If a cancellation is pending when this function is so you can explicitly do it, then the calling thread is terminated. It's kind of like the Go runtime scheduler. You can say runtime.schedule to do an explicit point where you check in with a scheduler to say, hey, do you want to make a scheduling decision? If you're in like a hot loop, like a CPU bound loop. And I guess, yeah, okay. Pthread test cancel. Sorry, I'm on the wrong page. There we go. A thread that is executing code that does not otherwise include cancellation points can periodically call pthread test cancel to ensure that it responds in timely fashion to a cancellation request sent by another thread. Cleanup handlers. If a thread with a pending cancellation were simply terminated when it reached a cancellation point, then shared variables like and pthread objects, e.g. mutexes, might be left in an inconsistent state, perhaps causing the remaining threads in the process to produce incorrect results, deadlock, or crash. To get around this problem, a thread can establish one or more cleanup handlers, functions that automatically executed if the thread is canceled. A cleanup handler can perform tasks such as modifying the values of global variables and unlocking mutexes before the thread is terminated. Each thread can have a stack of cleanup handlers. When a thread is canceled, the cleanup handlers are executed working down from the top of the stack. That is, the most recently established handler is called first, then the next most recently established, and so on. When all the cleanup handlers have been executed, the thread terminates. The pthread cleanup push and the pthread cleanup pop functions respectively add and remove handlers on the calling thread stack of cleanup handlers. This is what they were talking about before. I think this is silly. Just disable cancelability during the critical section. The pthread cleanup push function adds the function whose address is specified in routine to the top of the calling thread's stack of cleanup handlers. The routine argument is a pointer to a function that has the following form: void routine, void star arg, code to perform the cleanup. The arg value given to the pthread cleanup push is passed as an argument of the cleanup handler when it's invoked. This argument is typed as a void star, but using judicious casting and other data types can be passed in this argument. Typically, a cleanup action is needed only if a thread is canceled during the execution of a particular section of code. If the thread reaches the end of the section without being canceled, then the cleanup action is no longer required. Thus, each call to pthread cleanup push has an accompanying call to pthread cleanup pop. This function removes the topmost function from the stack of cleanup handlers. If the execute argument is non-zero, the handler is also executed. If the execute argument is non-zero, where does it execute? The handler is also invoked. Okay. This is convenient if you want to perform a cleanup action even if the thread was not canceled. So you pop it off the stack and run it anyways. Although we have described the pthread cleanup push and pthread cleanup pop, As functions, Custody permits them to be implemented as macros that expand to statement sequences that include an opening curly and closing curly brace, respectively. Not all Unix implementations do things this way, but Linux and many others do. This means that each use of the pthread cleanup push must be paired with exactly one corresponding pthread cleanup pop in the same lexical block. On implementations that do things this way, variables declared between pthread cleanup push and pthread cleanup pop will be limited to that lexical scope. For example, it is not correct to write code such as the following: pthread cleanup push if con pthread. Yeah, okay. I actually do like this a lot better than what I thought it did, which was having some like memory and some freaking global area that, or thread local area that's like a linked list or a stack of some sort. I'd rather it be on the call stack itself, which the lexical nature of these macros enforces that it's on the call stack. It's lexically scoped. As a coding convenience, any cleanup handlers that have not been popped are also executed automatically if a thread terminates by calling pthread exit, obviously, but not if it does a simple return. Oh, interesting. Example program. The program listing 32.2 provides a simple example of the use of cleanup handler. The main program creates a thread whose first actions are to allocate a block of memory. All right, 7:30 almost. I need to get through the rest of this. So we have our example program, and then we're almost done. Okay, I'm not going to read through their line by line stuff. I'm just going to review the code itself. So we have our condition and mutex and our global memory that we're protecting from them. We have a cleanup handler, a thread func, and a main. We'll just start with the main, I guess. So the main creates a thread, obviously. Goes to sleep for 2 seconds, and then cancels the thread conditionally based on argc. Does some global mutation, and then signals, and then joins. Okay, this is thread func that it spun up here. Thread func does a malloc of some buffer space, takes out a mutex lock, does its cleanup push of the cleanup handler, and then while it waits, basically it's waiting with the thing. Okay. Okay. I don't really care about this program. If we invoke the program listing 32 without any command line arguments, then main calls pthread cancel. The cleanup handler is invoked automatically, and we see the following. If you invoke the program with the command line argument, then main sets global equal to 1 and signals the condition variable. The cleanup handler is invoked, and we see the following. Asynchronous cancelability. When a thread is made asynchronously cancelable, cancelability type set to asynchronous is made. It may be canceled at any time, at any machine level, machine language instruction. Delivery of a cancellation is not held off until the thread next reaches a cancellation point. Problem with asynchronous cancelability is that although cleanup handlers are still invoked, the handlers may have no way of determining the state of the thread in the program listing 32.2, which employs the deferred cancelability type. The thread can be canceled only when it executes the call to conditional wait, which is the only cancellation point. By this time, we know that buff has been initialized to point to a block of allocated memory and that mutex has been locked. However, with asynchronous cancelability, the thread could be canceled at any point, for example, before the malloc call, between malloc call and locking the mutex, or after locking the mutex. Cleanup handler has no way of knowing where the cancellation has occurred or precisely which cleanup steps are required. Furthermore, the thread might even be canceled during the malloc call, after which chaos is likely to result. As a general principle, an asynchronous cancelable thread can't allocate any resources or acquire any mutexes, semaphores, or locks. This precludes the use of a wide range of library functions, including most of the pthread functions. Susci 3 makes exceptions for pthread cancel, pthread set cancel state, pthread set cancel type, which are explicitly required to be async cancel safe. Oh, that's a new one. There's async signal safe, and now there's async cancel safe. That is, an implementation must make them safe to call from a thread that is asynchronously cancelable. In other words, there are few circumstances where asynchronous cancellation is useful. One such circumstance is canceling a thread that is in a compute-bound loop. Summary. Okay. The pthread cancel function allows one thread to send another thread a cancellation request, which is a request that the target thread should terminate. How the target thread reacts to this request is determined by its cancelability state and type. If the cancelability state is currently set to disabled, the request will remain pending until the cancelability state is set to enabled. If the cancelability is enabled, the cancelability type determines when the target thread reacts to the request. You could use the asynchronous cancelability if when you enter a critical section, you just disable cancelability. Like you just say, hey, I'm going to temporarily disable the ability to be canceled, and then I enter my critical section, do all my business, and then I re-enable it when I'm done. And then you can cancel me asynchronously however you want. He didn't cover that. I was hoping he would cover that method. And that prevents, you don't have to use all the stupid cancellation functions. These cleanup handlers. You don't have to use these cleanup handlers and push and pop them off and do all that silly stuff. It's like just disable cancelability, do your critical section, exit cancelability. If the cancelability type determines when the target thread reacts to the request. If the type is deferred, the cancellation occurs when that thread next calls one of the number of functions specified as cancellation points. But Susci 3, if the type is asynchronous, cancellation may occur at any time. This is rarely useful. A thread can establish a stack of cleanup handlers, which are programmer-defined functions that are invoked automatically to perform cleanups, storing the states of shared variables or unlucky mutex. If a thread is canceled, further information, refer to the sources of further information. Okay. Cool. That is it. We are at 681. I'm just going to log that here as 681. And it is 7:31. And we are done for the night. I'm going to get LGA 2. So we need to do 29 first. So Vim readme. Just gonna say 29 is done. 30. We got a few. We got all the way up to 32. I was not anticipating cruising through all this stuff. So 20, 30, 31, and 32, and 33, which is not done yet. 33 is threads. Further details. So we have our introduction, thread synchronization, thread synchronization, and then thread safety, and per thread storage. And then here is thread cancellation. So all of these are done. Oops. So we finished what, 29? We finished up to 32. Git status, we'll do git add readme, git add chapter 29 and chapter 30, git status. That's all fine. and I'll just do get LGA1, get CIM, finish chapter 29, 30, 31, 32. Cool. That is it. I think I don't have my SH key added, so I'll do that in a bit here after I'm off. But I can say, I'll say T7 done, T7 done, T7 done, T7 done. That is 49% complete. I'm gonna call it 50% because I think it's just off because I added some extra tasks at the end of this task list. So that's 50% complete. Alrighty, I'm gonna hop off here, get to bed. I'll be on tomorrow morning to resume reading chapter 33, Threads Further Details. And in fact, we'll briefly, before I hop off here, we'll just go over what we have in the future here. So 680, so we're going to 780 tomorrow, probably. Ideally, maybe a little bit further. So it's going to be thread further details. Process group sessions and job control. I'm not super, I mean, the thread stuff, see, this is what the thing is. I was really interested in this stuff, but I knew a lot of this stuff already, so it wasn't really difficult. Whereas this stuff is going to be difficult because I don't really know this stuff because it doesn't interest me. Process groups, sessions, and job control. Like, it's a bunch of shell stuff, process groups. But I guess it's good for me to know. So yeah, threads further details. What's in here? Thread stack, signals, process control. Advanced features of pthreads API. Maybe that'd be interesting. Process group sessions, job control. Process priorities and scheduling. That's like the nice stuff, yeah. Process resources. So these are the limits. This is actually something I need to, I mean, it's like writing ulimit is like what I've about the extent of like what I've encountered. It's like when you're running into a limit, you just set ulimit and it sets it for the child processes. Daemons, like obviously I know what a daemon is, but like be nice to go over that. Okay, so we got one more chapter on threads and some details, maybe some advanced features, and then a bunch of like stuff that is like, I don't know, not terribly interesting, but not that crazy. Nothing that makes me feel like I can't read 100 pages tomorrow. So tomorrow is Friday. I have the entire day free, so I will be on tomorrow to read at least up until 782. So yeah, we're cruising. All right, I will be on tomorrow then.